Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
All right, everybody, let's go ahead and get started. Welcome, everyone. Wonderful to see you in person here. Welcome to the session, Back to the Basics Pointers. And my name is Mike. I'm going to be with you the next hour or so. For folks online, feel free to submit questions, and we'll try to get those answered, as well as folks in the audience. We've got a great audience here, so just go ahead and dive in. So here's the abstract that hopefully brought you to the session here. So you've already read that or taken a look. The code is also available, so don't worry about that if you'd like to take a look later. My name's, again, Mike Shah. Primarily, I teach, and I also work as a consultant for various 3D graphics projects. So that's sort of my domain. So you can read more about me on my website here as well. Now, I want to start this off with one of my fondest programming memories. And that was when I used a pointer correctly on the first try. And I sort of remember this sort of eureka moment when this happened. And it was about my sophomore year of college, I think, if I'm being honest, where I was learning C++, and I wasn't just guessing where to put the asterisk or the ampersand. I had actually written some small sort of toy examples like this, and that's what really helped me understand how do pointers work. Okay? But you know, the truth be told, it was probably in graduate school, so a few years later, that I really understood the power of pointers. So kind of putting everything together. I had some systems, domain knowledge. I could actually teach someone else what a pointer was. And then even post-graduate school, I sort of think of them in a different space, sort of thinking about ownership and lifetime, or levels of interaction, these laws, good practices for software design, memory safety. So you know, that's where the journey sort of takes you. But in this talk, I want to make pointers not scary and just show their usage. A lot of small examples like how I learned pointers. So I also want to show you how to use them and how to avoid some of the potential pitfalls that you can have with pointers, different memory errors or problems that you could have. And also just to appreciate that we have pointers in C++ and that they're really, really powerful. Now, my disclaimer for folks who are in the audience, online, or watching this later, or here with me today, you know, this is an introductory level talk, and I'm going to be talking about raw pointers. And you know, I don't want newcomers to the language to get scared of pointers here. But I do want to show how the fundamentals work and try to break things down. And for experts in the audience who can pitch in before or after, I think it might be interesting just to see how I teach this or approach teaching it. So you can share that with your team members, students that you work with, folks that you train, and so on. So, you know, let's start from the beginning. Just what is a pointer? And maybe not the very, very beginning where, you know, the 50s where pointers were invented, but at least the beginning in C++. You know, what is a pointer? Well, a pointer is a variable that stores the memory address of a specific object type. Okay, so let's again look at that example that I was very proud of many years ago. This sort of example here. And here's my actual pointer here, px, and that's a pointer. And it's an integer pointer, so it can store addresses of other integers. Okay, so that's the first portion here. And, well, how do I store an address? Well, I have to retrieve the address from a piece of memory or some other variable. So I can use ampersand of x to do that. And ampersand, you can think of like a operator, or if it's useful, you can think of it like a function here. If you put ampersand in the parentheses and the thing you're trying to get an address of, and that stores effectively the address of x into px here. And the assignment operator here is, again, what's doing that assignment. So it's storing in p of x, the address of x. So some value where x lives. So what's neat about this is if p of x stores the address of x, then we can indirectly access this value that x stores, 7. Okay, so it's clear that that's what that's printing off. And again, with these sort of toy examples as you do them, it's very helpful to, you know, as you're learning, just print off what the actual values are. Okay, so here we can see p of x is the second thing that I'm printing off, but there's this weird sort of asterisk symbol here that is going to get used multiple times in pointers, and we'll again clarify that. And that's something called dereferencing, where we can actually get the value of the thing that we're pointing to. Okay, so and here's the actual example that is running. Okay, so clearly the star p of x is accessing the value of x, and we return the same value 7. Okay, so what's really helpful with pointers often when I'm is to try to visualize them. I'm going to let this animation play through once here, and again, so you could rewatch it if you'd like. But it's always useful to draw pointers because you're effectively pointing to things in memory. So that's how I want us to think about pointers. Okay. So I'm going to let this little animation finish, and then again, we'll watch it one more time and walk through it. Okay, so there's the arrow going. We're pointing to something. We'll figure out what that means. And then an address here. Okay, that's what it stores here. Kind of a weird address. Maybe it's would be an even number, but that's okay. Okay, so again, often trying to draw these things out is very useful. So again, take your toy examples, take a small program here, and try to draw out what's going on here. So int x equals 7. Well, somewhere in memory, 7 is stored, and that has an address, and we can write the sort of associated line of code here. And then the next part of this was creating our pointer, so int with a star next to it, that's the pointer type, p of x, and we're assigning it to the address of x. So if we're doing this assignment, well, what are we storing? It's the address of something. So that's why I'm sort of putting this arrow here and following or chasing towards this address here, 0x1001. Okay, so this is what we get here. And again, the tip is, as you're learning pointers or even debugging pointers if you're an expert, is to try to draw it out and see if what your code is doing matches your assumption of what's on your drawing. So again, let's let this play through and just kind of step by step walking through carefully what's going on. Let's let it rewind here. All right. Took me about 10 takes to get the actual animation here, but so when we start off when we're just creating our variable, that's sort of creating the box, the storage. There's nothing in it, but that exists somewhere. Okay, and then once we do the assignment, then we're putting 7 into the box. So that's what's going on there. And then we're creating our pointer here, our pointer type, int star, p of x. That's got an address too because, well, it's storing something. Even if it's an address, that's okay. It still has its location in memory. What's it storing? That ampersand symbol, ampersand of x, and we point to the address of where x lives, okay? And that's the important part. So that's what is stored in memory. Okay, so again, I'm talking a lot about memory here, so I want to, again, visualize what's going on here. So we saw the little hand drawing, but just to have another concrete example here, when we're working in pointers, we're often thinking about memory. Now, there's many different layers of memory, whether you're thinking about registers, cache, hard disk, maybe even cloud storage. But for now, let's just assume everything's in sort of our working memory, our dynamic memory, or our DRAM. So we can think of our memory here as stored in one of these sticks of RAM, and it's just sort of listed off one address after the other, this sort of linear array or linear listing of memory. Okay, so I've got my addresses here, and then I want to store some values. And depending on the type of data that I'm storing, meaning what type of an integer or a float, I might need different numbers of boxes to actually store that value. Okay, so let's go ahead and store something like int x equals 7 here. Okay, so I need, well, 4 boxes here. Why 4? Well, we have to sort of figure that out for our machine. What does it mean to store an integer? On my particular machine, it means 4 of these boxes or 4 bytes, where each one of these boxes is 1 byte or 8 bits. Okay, and we don't have to leave this to guesswork here. In C++, it provides us a really handy operator, size of, and I can put in the data type here, int, to figure out its size here. So the printout leads us to 4 here. I could also put size of x here if I just want to put the actual name symbol or the variable name, and that would be okay as well. Okay, so what happens to our pointer? Because that was something that was also in our drawing that we had to lay out. Well, that needs to be stored in memory as well. And because we're pointing to the address of x, this is what it looks like to store it. So it gets put somewhere in our memory here, and we're pointing to, well, the address at which x starts here. Okay, so 0x1 followed by 7 zeros. And remember, p of x here, which is an integer pointer, so I have int and star, the integer pointer type, stores the address of the variable that it points to. But when I dereference it, so when I use that star here, or asterisk p of x, I'm actually following the address here and then retrieving the value. So you can, again, follow the arrows here. OK, so this is what we have. Now, I've used this term dereference a few times, so I want to, again, just clarify that term. All right, so let's see what it means to dereference a pointer. And again, the vocabulary often is a place where I see beginners get confused with pointers, because there's going to be a lot of different vocabulary. So when I say I'm dereferencing a pointer, that means access the address stored in our pointer and access the value pointed to by our pointer. So again, follow the arrows into the actual memory and retrieve the value. OK, so if I'm dereferencing a pointer, as we've previously observed, that's where I had this star p of x here, towards the right side of the screen here. That's dereferencing. And again, in a plain sort of English sentence to follow along that says, if the type of my variable is a pointer, which it is, int star or int asterisk, I will retrieve the value at the address at which I point to. Again, just retrieve the address stored in the pointer and get the value. OK, so note on this asterisk, because again, it's appeared 2 times in sort of 2 different contexts, and I don't want you to have to guess where it goes. So the first part is with the type. So for me personally, or stylistically, I like to put the asterisk right next to the int. You can do it either way, but I like to think of it as together with the type. And I also like to, when I'm naming my variables, prefix them with a p. That's why I've had px here. It just helps me remember that this is a pointer variable. Most of your IDEs or tools might help you with this. And then again, the second use of the asterisk, just to be clear, is when we're dereferencing. And that comes before the variable name here. So I'm trying to retrieve the value p of x here. OK? All right, so all the things that we've seen in a slide, just so you have them. And again, working out toy examples, because this is how I was able to learn it, this is how I'm usually able to teach it, is just to, again, try to print out what's in the actual variables, or the address of something, or when you try to dereference something. OK, so here's a little example with everything that we've learned so far. OK, so again, p of x is pointing to the address of x. Pointers store addresses, and we can clearly see x's address matches the thing that px points to. So again, this is the other trick to just sort of print it off and to see the actual addresses. If you go line by line, you can see that. OK, so dereferencing, again, p of x should retrieve us x's value. So we can look in this toy example what's stored in x and retrieve that value. All right, so a little test for my folks in the audience here, if you can see the code, is to think about what happens here. So if we have an integer, int x equals 7, p of x is pointing to the address of x, and then if I dereference p of x and assign it to 42, what's the value going to be? So go ahead and make your predictions in your head or online, or pausing if you're watching this in the future. Does anyone want to signal with fingers or anything what the answer is? All right, I see somebody mouthing it. It is going to be 42. OK, because again, we're following our pointer, or the box of memory of the thing that we're pointing to, and assigning it to 42 here. It might be a little bit helpful to think of it in this way, where I can put parentheses around this operation. I don't have to. The asterisk here, when I'm dereferencing, has a higher level of precedence, but this might be just a little bit clear, again, if you're starting off with pointers and these sort of toy examples. But I'm following, saying, hey, retrieve me this value here, which is x, the thing that lives at where p of x is pointing to, and setting that to 42. All right, so that one wasn't too bad for folks here in the audience. But what about this one? So we can kind of increase our level of difficulty, or the level of indirection here. So just to sort of walk us through here, I'm initializing an integer, just like we're doing, x equals 7. And then I create my pointer, p of x equals the address of x. And then I have this other thing here. Two asterisks. And then I have p underscore p of x. So I have a pointer type here to a pointer, okay? And I'm pointing to the address of, well, this has to store integer pointers here. That's the first part. And then the next asterisk is saying, hey, make this type a pointer. It points to pvex here. Okay, so this is 2 levels of indirection, which we can also do with pointers. So we've, in a sense, made a chain here with one pointer pointing to another pointer, finally pointing to x. Okay, so I'm going to give this one away here, and we can look at the actual code and try this out. But depending on the levels of indirection you have is how many asterisks you use, in a sense here. So just to pick on one of these examples here, this third one here, if I have star pvex or asterisk asterisk p underscore pvex, well, the first time that I dereference p underscore pvex, that's giving me pvex. And if I dereference it again, I'm following what does pvex point to, and that points to x, dereference that value, and retrieve it. Okay, so that's pretty cool. That's pretty powerful, something that we can do with our pointers. Okay, so why is this a big deal, though, that I can sort of dereference things or have pointers to other pieces of memory? Well, in this example, what I'm really showing is how I can share data and from multiple locations where we can retrieve the same value. So, I'll push the boundaries here of what I can show on a slide here for a moment, but again, I'm allowed to do that if I walk you through it slowly. So let's look at another example that really demonstrates sharing here. Okay, so let me walk us through this slowly, something new here. So this time we've got some structs here, and I've got a struct person. That's really the important part here. And we're just going to store a nickname, okay, for that person, whatever their preferred name is. And then I've got a company here, and they have a pointer to their CEO. Okay, just one person here. It's a simple company. And then our friends here, who have a pointer to one friend here. Maybe we should extend that list, but just one for now to keep it simple. Okay, so 3 data types here, and 2 of them store pointers. All right, so if I go ahead and start this off, well, let me create a person, Michael, that can be me here, and set their nickname to Michael. And then I'm going to create a pointer to another person, my fake twin brother, which I don't have, but the pointer to them. And then also a company, my employer, and friends, my friends, or my one friend. All right, so let's initialize our pointers and, again, demonstrate what I'm trying to show here, that we can share data with pointers. So my fake twin brother, well, that's a person pointer, or a pointer to a person is how we read this. So it can store the address of Michael, who is a actual person here. And then my employer dot, so accessing the field here, the CEO, that's also a pointer here, person, and that can point to Michael here. And the same for my friends here. Okay, so I've got some sharing going on here with my fake twin brothers pointing to Michael, the CEO, Michael, friend, also pointing to Michael. So all the same location. So now if I update my nickname, I'm going to do this through Michael, and do michael.nickname equals Mike. Well, what happens is, in effect, everything that's also pointing to Michael has been updated. So I've only done one sort of write here, one update, and the value will be, in a sense, updated in those 3 other locations. Okay, so when we do this, my fake twin brother is also Mike, my employer should call me Mike, and my friend should also call me Mike. All right, and here's all the code for you to review as you please. Now there was a subtle syntax thing here. And I will rewind us back here, because you'll notice I printed out my fake twin brother 2 times here. We only had 1. Now, why did I print this out 2 times here? Well, when we're accessing the field here, we can actually use a syntax that's the arrow syntax. It's a little bit of a syntactic sugar here. But what it means is that we're dereferencing a field, and, dereferencing our pointer and then accessing the field. Okay, so my fake twin brother, let me go ahead and just walk it back here, was a person. A person has a field that's their nickname. So normally if I want to access that, I would do dereference my fake twin brother and then dot nickname. And that's a little bit of a syntactically hard thing. There's more symbols, more things to type, more room for error. So in C++, or really adopted from C, we have this arrow syntax, which means dereference and access this field here. Okay, so just a subtle syntax thing, and this is sort of the preferred or a cleaner way to see things. Okay, so we have our basic tools of pointers, and I sort of understand this idea that pointers are about sharing data. Let's see what happens if I pass pointers into functions. Okay, so I'm going to have two functions here. And again, I'll try to walk you through slowly. But the difference is one of these takes in just an integer, and the other takes in a pointer to an integer here. And I've sort of named them appropriately here, int pointer, and this one's just x. And then you'll notice that these functions are also used in a particular way. I create two values here, int x, int y. I'm going to pass x into the pass by value function, and pass by pointer, I have ampersand y. Again, why is it the ampersand here? Well, this needs to store an address as its parameter. Okay, so the first one is, well, as its name, pass by value, which is really a type of semantics for how we pass data into functions. And what we're doing here is we're making a copy of this value x, and that's what is being stored as I send x into this function. It's a copy. Okay. And in the second version, I'm doing pass by pointer, which is, if we're being technical here, the semantics, it's still pass by value. Except remember the thing that it's making a copy of here is, well, actually stored in a pointer here, and pointers store addresses. And those addresses could be anywhere in our program, right? As long as we can point to that memory. So for my audience here, and for those who want to pause and take a moment to think about this, what do you predict the output of x and y at lines 17 and 10 are going to be here? Okay, so let's see. At line 17, and line 19 here. So hold your guesses. I see somebody is gesturing a 5 here for x. Okay, so it would be unchanged. And then for the other one, I see 9999. Perfect. So, and again, why does this happen? Well, this is showing the power that this is storing an address. And it's storing the address of the thing that's at line 15 here when we're passing by pointer here. Okay, so again, pass by pointer is really pass by value, except we're mutating the value through the address that the pointer stores. Okay, and I like to give this a different name. So depending on the text you'll read, you'll see this introduced as pass by value, and then we sort of explain the semantics, but I really like to think of it as pass by pointer. And you're going to see this sort of pass by pointer style very common in C style APIs. That's what you have when you want to pass data into a function and mutate the data. So that's sort of your option. Now, sometimes in these APIs, this is just sort of a note here, things can get a little bit excessive, where maybe you're passing in lots of different pointer values here. And maybe you have some of these that are going to return out values. And in general, that's something to be careful of. There was a talk a few years ago from Jason Turner who mentioned this might be a potential code smell. So you have to be a little bit careful with this style here. And another subtlety here with pass by pointer, if you're okay with the idea of how we're able to change the value through the address, remember it still is pass by value, so we can't reassign the pointer to something new within this function. So if I go back to our previous example, if I reassign and just do int pointer equals some other address, well, remember this is still a copy, so that change isn't going to be propagated. So we do have to be a little bit careful about that. Okay. All right, and for, of course, my C++ folks here, don't worry, I will mention a pass by reference towards the end and why we might like that. Okay, so we've got our pointer variables, that's checked off. Dereferencing, that's checked off, or sort of understand these terms. Pointers as parameters, that's also allowed, that's totally fine. Now let's also talk about pointers versus arrays, because again, we're thinking about memory, and of course, the folks watching this have probably seen arrays, and that's where you can store things in memory, in a contiguous chunk of memory. Okay, so pointers and arrays. And again, I just want to visualize some memory. Nothing's really changed. It's still a linear address. I'm just going to represent it as a grid because I need more space on the slide here. So these are all contiguous, or one giant table with one column, if you like to think of it that way. Okay, and again, the types of data that we store have different sizes, including if they're user-defined types. And again, we want to use size of to figure out how many bytes in memory that those items take. Okay, so here's just an example on my 64-bit machine. And again, if you have a different architecture, these types might be different for you, so you have to check. Okay, so here's just a few examples using those sizes and to see where things get placed into memory. So I have an int, a char, and a float. And ints are 4 bytes, chars 1 byte here, and 4 bytes for the float. So those might get arranged like this in memory. Okay, so what happens when we create an array of data? Okay, so in this example, I'm going to allocate 6 shorts in a contiguous byte. Short on my machine is 2 bytes, so that should give us 12 bytes allocated. So 12 of these boxes are filled in here. Okay, and because it's an array, it's a contiguous block as well. Then, of course, we want to initialize our memory. That's always good practice. We want to initialize things that we create. So I'm just going to set everything to I for now. Okay, so then we see something like this. So now if I create a pointer to a short, so short and then the asterisk, and I'm going to call this p_s, again, p the prefix indicating that's a pointer. Based on what I learned, I should be able to point to each of these individual elements here. Okay, so I'm going to do just that here, set up my pointer here. And my pointer takes 8 bytes on my system. I have a 64-bit machine, and I need to be able to address any of those 64-bit addresses. So I need 8 bytes of memory to do that. And if I want to point to one of these elements in our array, well, I can take the address of the array at index 2. Okay, and that points me appropriately to the second index. Okay, no problem there. And I can update my pointer just as previous, as long as it's pointing to other data that's a short. No problem there. Address of array at 3, and here we are. Now what happens if I try to increment a pointer? Well, we can actually do that as well. So here on line 13, I have my pointer to a short, and I'm going to assign it to the first index of our array. That was how we previously did this. So I'm at the first item here. And then if I increment p of s here, doing plus plus, or I could do the pre-increment as well, it moves the pointer to the next item. And then if I do it again, it moves to the next item, and the next item, and the next item, and the next item. And that's pretty cool. Now, why does it do that? I'm only adding 1 here. I only see plus plus, and last time I checked, that means just add 1. So what's happening is, with pointer arithmetic, because the data type is 2 bytes, when I add to a pointer, or do plus plus, that's going to shift me over 2 bytes. Okay, and this is one way that I can, in a sense, walk through this array. Okay, so note on arrays as well, since we're thinking about sort of offsetting, as I was showing here, just moving one item at a time here. The number of times that I was incrementing p of s was moving us through the array. And we can actually do this with our array here. So I'll show the example in the bottom right corner, where I have an array. And if I add 0 to it and then dereference that value, I'll get the element at the 0th index, or our first item. So what this is really showing here, and this is just to confirm the results here so we can see it, is that the bracket notation that we use in arrays is really a shorthand for dereferencing and offsetting this. Okay? And we can think of this in this way. So array is just the pointer, and then we're adding to it how much we want to offset, and then retrieving that value here. Okay, so again, and because an array is just a contiguous chunk of memory, we know for moving, say 2 bytes at a time in the example with our short, that we're able to do this and get to the correct offset and read the appropriate value back. Okay, because arrays are a homogeneous data type. Okay, and we can even, I've shown this where we've sort of incremented forward, we could increment backwards. We do want to make sure that we're within bounds, so within 0 and however big that array is. So I do have to be a little bit careful, but we are allowed to do this. Okay, now there's this other idea with, are arrays just pointers or are pointers just arrays? Because if everything's just memory, what does that really mean here? Okay, so when I was doing this traversal here, in a sense, when I was doing p underscore of s here, so our pointer to a short data, we're almost losing some information about our array here. Because I'm just saying, hey, treat this address and move it forward 2 bytes. And a way to sort of confirm this or to think about this is if we, again, use our size of operator that we had, is if I just take the size of array with no subscript here, or the indexing any element, versus the address of the array here, I get different values here. Okay, so we actually have a sort of pointer type and not an array here. Okay, because I'm accessing the address of something here, so that must be a 8-byte value versus the array, which when I have this array here, I know it's 6 shorts, which was 12 bytes, right? We saw that in our visualization. And if this is a little bit confusing, one way that you can sort of think about this is, if you do an array here and try to assign it to a pointer, it's not going to let you do that. So, these are different things, arrays and pointers. But if I take the pointer and assign it to, again, the address of one of the elements, that's a short, because it's a pointer to a short, this is allowed. Okay, so this might be one way to sort of disambiguate as we're thinking about pointers versus arrays. Okay, so what does this mean if I try to pass pointers as parameters into functions? So we've already looked at one way to do this when we were passing our int pointer and learned about pass by pointer. But what if I want to pass a chunk of data into a function? Okay, and think for a moment to yourself, what does this actually mean? Again, what information do we lose when we try to pass an array into a function? Well, in this case, the array does decay to a pointer when it's a function parameter here. So I've called this function array decay, and I'm just passing in a pointer here. Okay. Okay. So in this example, we can try to look at the size of the types to try to get some insight to see what is this actual type that I'm passing in again. Now, I would probably prefer anyway to, if I'm passing arrays and so on into functions, maybe prefer a vector or some other data type so you can retrieve some of that dimensionality, because you want to know how big this collection is, right? How many elements can you iterate through? So this is one way to do it, is to just pass the size of your collection as a second parameter. And then you can utilize your array as needed. And you'll see this very frequently if you've done any C programming prior to your C++ or after, where you pass in the size. I do have a little bit of a wilder slide here. This is just an aside to show another way you can do this if you really don't like passing parameters. Just for fun, you could pass in a template parameter here, where you figure out what the size is of the collection beforehand. So I'm looking at line 21 here, and I do it again at line 18 here, where I just calculate the array.size. Okay, so that could also be one way to have print array without size parameter and just pass in the array, but I don't know how long it is. Does anybody like this solution in my audience? It's a little bit wilder. Yeah, probably not good. So we want to be careful with going too wild, but I thought it was kind of a fun example. You can actually print out the code to see it's generated and see you start generating functions for every different size of arrays you have. So that's probably not good. And it's also fun just to know how you can print out what syntax is actually being generated. So you can use your compilers to do this. All right, so there we see one for the actual function, one of size 11, one of size 10. Oh no. Okay. All right, so let's stay focused here and get back to arrays here and talk about dynamically allocated arrays. Okay, because this is another cool thing about pointers is, we actually just need these because when we're pointing to a chunk of memory that's dynamically allocated, well, we have to know or have a handle to that memory. So pointers in a way are necessary for that, right? If we're going to ask for memory while our program's running. So here's an example, and I'm going to use new in C++ to do that. And we want to dynamically allocate some memory here. Okay, so just as a refresher, the same rules apply with working with arrays here. So let's look at a little example here. So here at line 10, I have a int array here. And I'm going to point it to this chunk of memory here that gives me 3 integers. Integers on my machine are 4 bytes, so 12 bytes total. And when I'm done with my memory, I also need to make sure that I free this block here. So I delete it. Okay, and I use the brackets to delete the entire block. Okay, so just walking us through here, we create our pointer. That's got to go somewhere in memory. So the int pointer has been created. Again, 8 bytes because we need to store any type of address. And then my 12 bytes of memory. Now, I could have maybe laid these out right after, but we don't know necessarily where the memory is going to go. It's going to go somewhere, and our operating system will choose. But the int pointer will point to the first element in this block of 12 bytes that we have. Okay, and these are uninitialized, so we don't really know what values are here. Okay, and this is an example of heap memory. So again, with pointers, we're also thinking about where our memory is going, stack in the heap. There's a few CppCon talks I'm going to link to at the end if those terms are unclear for folks, and you can check those out. All right. And just a note, and we're going to see this as one of the pitfalls of pointers, is that we have to be careful when I delete. So I'll draw your attention to these our array here that we've allocated. This is still sort of filled in here, but we don't really know what's in here. It could be garbage, it could be zeros, we don't really know here. So we'll have to think about what dereferencing an unknown value means. All right, so let's look at this in round 2 here, another example. Here this time I've kept the same thing that I had previously here, where I have our int array, allocate 3 integers in a dynamically allocated array. I initialize them, and then I create another pointer and point it to our int array. Okay, so in effect, I again have 2 pointers pointing to the same piece of data, and then I delete the data, okay, as I previously did. And then we try to use the memory after it's been freed. Okay, so line 18, and I've got a little comment here, it says, uh-oh. What if we try to work with int array too? Because it was pointing to int array, but, well, at line 15, we said, hey, delete that memory int array. Okay, so, what happens here? On my system, it does something like this, where, well, when we started, we were okay, and we had a bunch of values that were initialized, but then when int array got deleted, now we just have 0 here. Okay, so, when we're doing sharing, we have to also think a little bit about who owns the memory. Was it int array? Was it the second one? Were they reassigned anywhere? We do have to keep track of this, and we'll introduce some ways to do that to make life a little bit easier for us. Okay, so this concept of, does a pointer have to point to anything, or what if it points to nothing? We have this idea of a null pointer, okay? So a null pointer, from folks coming from a C background, is just like a value of 0. In C++, that's a little bit stronger. We have this actual sort of type here, null pointer. Okay, so let's actually look at an example. And the piece of code I'm looking at here is at line 7 here, where I create our integer pointer, p of x, and I assign it immediately to null pointer. Because again, we should always assign our variables when we create them, otherwise, who knows what the default values are. But what happens here is, well, I go down to line 11 and I try to use this pointer in the sense that I'm dereferencing the value. And dereferencing null pointer or something that doesn't point to anything actually gives us a segmentation fault or an error, right? We're trying to access something that we don't own. So the safest thing for my machine to do is to crash at this point, and you get segmentation fault. Okay, so a tip is with your pointers, you're going to have to check to see are the values null or this null pointer type before you attempt to dereference. Okay, so that's one way to protect yourself from this crashing or segmentation fault. Okay, and this is sort of leading us into some of the pitfalls of pointers. So again, I've said pointers are powerful. In fact, the original title for this talk was The Power of Pointers. But with great responsibility comes great power or well, whatever it is. We have to be careful with our pointers. Okay, so again, the common pitfalls of pointers, and again, I try to think of this in different ways. Now I think of it in terms of ownership or sharing. And if you're coming from your first time looking at pointers, maybe you'll just think of these as sort of different pitfalls or errors that you can check for. And that's also okay. So in roughly one slide or so, I'm going to show you some of the common pitfalls of pointers. So the first is what's known as a memory leak. And it's when we forget to reclaim our memory. So on the right here, I've got an example where at line 10, I allocate 1,000 new integers, an array for that, okay? And then I also have this while loop here where I'm just doing lots and lots of tiny allocations. Forever, forever, forever. And then, eventually maybe this program terminates, right? Or I kill it, but I've never deleted my memory here, okay? So we call this a memory leak. We're not returning memory that we've finished. So, eventually the operating system will clean this up, but if you have a long-running application, a game, a web server, whatever it might be, you're losing memory here by doing this. Okay, so we need to be able to reclaim our memory when we're done with it. So there are some handy tools that can help you check for this, because again, right, these are the sort of toy examples that we want to see to get familiar with the problems and practicing with pointers. But as our programs scale, and we're thinking thousands, tens of thousands, million-line code bases, we have a few tools that can help statically or dynamically check for these errors. So there are the address sanitizers available with the compilers. So I've got one example here of how to run that with Clang's address sanitizer. And another tool, if you're a Linux or POSIX user, Valgrind, not Valgrind, but Valgrind is the pronunciation. That'll also tell you where you forgot to delete your memory. So you can get a little trace here. We'll say, okay, you're doing something with new, and you got the brackets here, and uh-oh, at line 9, you forgot to delete that memory that you allocated. Okay, and you should compile your programs with debugging symbols to help these tools with -G here. Okay, the next type of problem is what's known as a dangling pointer. And that's when we point to memory that doesn't exist for some reason or another. Maybe it was deleted, maybe another part of our program deleted it, or maybe it just went out of scope. So in this example, I've got a function here. It's at line 5, it's called dangerously return local value. Okay, so what's that doing here? At line 6, I create a character. It's local in scope, and then I return the address to that character here. Okay, and then I have at line 12 in a different scope. So this is sort of your warning here. Dangling pointer equals the address of the thing that's returned here. So maybe this thing's still in memory. Maybe it's disappeared. The problem is if we try to dereference this, we will get a segmentation fault. Okay, because we don't own that memory again. Okay, so we do want to use our address sanitizers in these tools to help us catch these things. When I compiled this with G++, this was version 7, it actually did give me a warning and said address of local variable C returned. Okay, so it is warning me about this very common problem. Okay, here's another fun one. This is called a double free. So a double free occurs when we're sharing data between 2 or more pointers. Again, that's something we might want to do with pointers. That's part of their power. And we are trying to be good. We are trying to free our memory. We say, OK, yeah, we're done with it. So we delete. So if I draw your attention to lines 8 and 9 here, I'm creating a pointer, allocating some floats here, a chunk of memory, pointing another pointer to it. And then I say, oh, OK, I'm done. And I delete F2 here, which points to F1. And then I'm even extra good. I assign it to null pointer just to make sure that it's null. It doesn't point to anything now. And then I go ahead and delete F1 because maybe I forgot or something else happened. And I also assign that again. And then maybe I delete again here. And this will cause the double free error. You might get an error that says error, double free, program aborted. Now, on my system, since I'm a Linux user, my runtime actually protects me from this, and I actually didn't see a crash on this type of toy example. So you do have to be a little bit careful, especially if you're developing for multiple platforms here. So if I change my allocator, my platform, and so on, I might not catch this error. But again, the sanitizer tools and some of these static analysis tools will help you catch them. Okay, and there are more of these sort of best practices related to pointers. So I don't want to overwhelm someone who's just getting started. Those are some of the common ones: null pointer, dangling pointer, double free, and memory leak. But the ISO CPP website has some nice discussion about memory management that I would draw your attention to. Okay, so how could we mitigate some of those bugs? Because I'm a C++ programmer, and one of the ways that we can do that is to add good abstractions that protect us and help us write better software here. So on the right, I have some code. I don't care that you need to read it, but all I want to draw your attention to is that I've created something at line 9 called the class Mike's safe pointer. Okay, so maybe there's some way where I can wrap these raw or plain or naked pointers, as they're referred to, and do something smart with them. So every time that I construct them, I make sure that they're set to null or allocate exactly once. And when I destroy them, I check if they're in use by any other pointer. Okay, now this can be a great implementation exercise, I think, to see what your sort of understanding is of pointers and memory safety. But luckily for us, again, modern C++, so 11 and beyond, provides us several different smart pointers. Okay, so I want to briefly introduce these smart pointer types to us. Okay, so getting smart with our smart pointers here. And again, what is a smart pointer? Well, there's 3 types that are given to us: unique pointer, shared pointer, and weak pointer here. And basically, they're a way to, again, wrap raw or naked pointers and control how they're used here. Okay, so they solve some of the problems where we might not have to call delete explicitly anymore. In some cases, we can even avoid calling new. We have member functions to do that. Make unique pointers, make shared pointers. And we're ultimately enforcing some type of constraint with each of these pointers and how they behave. So it is more to learn, but it's going to make our programs potentially much, much safer and easier to manage as they scale. So again, what are they doing behind the scenes? Or what was I trying to do in my Mike safe pointer class? Well, it might be doing things like reference counting, which is basically saying how many things are also pointing to me, or how many times am I in use? Or maybe you're able to enforce uniqueness. So for example, maybe you're not allowed to reassign one pointer after it's already been created and initialized. And maybe we can also do some other clever things in these sort of edge cases, like when we have exceptions and need to think about, well, what happens if we try to allocate a bunch of memory and get a exception for too much memory allocated on our system. Okay, so let me briefly show some of these examples in a slide so that you have them and the basic idea. Now there is a session on Thursday by Inbal Levi that I definitely recommend checking out that's going to expand or be a continuation of this talk. But just to give you a teaser for that so you can learn more, we have something called unique pointer. And this is a pointer, well, I've put it in scope here. So when it leaves this scope at line 24 to 29, this unique pointer that I'm creating, it'll automatically be deleted. So I don't have to worry about this new object that I've allocated. And this can be your sort of default go-to, just to make sure that you're really safe with your pointers, because again, it's going to take care of deleting the memory on its own. And we also cannot assign unique pointer to something else. It has to be unique. And just another syntax note on sort of style or tips that I've picked up is we tend to prefer, or I've tended at places that I've worked, from lines 34 to 36 to use this stood : make unique for our object, rather than having to explicitly call new. The second type of smart pointer is what's known as a shared pointer. And this allows pointers to have multiple things pointing to it. And as long as the other pointers are pointing to that memory, the memory won't be deleted. So this means if we try to use something after it's been freed, for example, well, if there are still references or, other things that are pointing to that pointer, that's okay. Our memory won't be reclaimed. Okay, so internally, this is sort of the idea of a reference count or a use count. And with the shared pointer, you can actually, through one of the member functions, see how many times it's being used. I think it's .use_count, and you can print that out. And the final type of smart pointer is one called a weak pointer. So it's very similar to a shared pointer, but it doesn't increase the reference count. So in this way, this allows you to have some invalid pointers. And you might want some sort of lightweight way to just create a pointer that points to something that you don't really care if it exists or not. In a use case, since I sort of come from games and graphics world, is maybe you have a game and then some object gets destroyed in the middle of the game, but you don't care if other players are still looking at that object or whatever. It's you want to be able to handle that and just check if it's null or in use or not, and that could be okay. Okay, so in this weak pointer here, it's just sort of like a temporary pointer that you want to point to something, and it's okay if it doesn't exist. Okay, and here's another weak pointer example, just so you have two in the slides, because I think this is sort of the more weird example, but I'm going to defer this to the end in the sample code. And I did lie, there was a fourth type of pointer that's gone, so you don't have to worry about it. Don't use it. Auto _ pointer. All right, so continuing on talking a little bit about pointers and functions, well, functions, they have addresses, right? They have to exist somewhere, so we can actually have pointers to functions as well. So on the right, what I'm showing on this screen, I know there's a lot going on, but at the bottom right corner, I've got two function names here, add and multiply. And I'm just showing or confirming that, in fact, functions have addresses. So it makes sense that we would be able to point to them through some mechanism. And of course, we can do this with pointers as well. So how do we create a pointer to a function, or as we call them, function pointer? Well, I've got the syntax here on the right here at line 14. And it's a little bit wonky, and I admit sometimes I have to look it up just to keep it straight. But you sort of work your way from the inside here, where I have PFM, so pointer to function. That's a common sort of prefix here, underscore, and this is my arithmetic function. And then on the right here, I have int. So this is going to be a function pointer to functions that have two arguments that are integers, and at the end here that return an integer. So that matches our signatures of add and multiply here. And you'll see that I can point to the function here, pf of n underscore arithmetic equals add, so it's now pointing to this add function at line 5, and then I can call it with arguments. And if I repoint this to multiply, I can also call that with arguments as well. All right, and this is our result. Now, modern C++ does offer something called std: function. And this allows you to store a callable object. Okay, so that could be a bunch of different things. But one of those callable objects that you could do, meaning something that you can invoke, would be a function. So here's an example here, just modifying just very slightly, just the part that's highlighted here in orange, for how to create a std function. So it's got the arguments here, int, int, and the return type there. And it's a little bit cleaner to use, in my opinion. Okay, so we're reaching sort of towards the end, and I said pointers were powerful, and they certainly are. So some other odds and ends for things that might fit in a full day course or for the future are listed here. If this gives you some things that you can sort of Google after mastering the things in this talk. I did mention that I would talk about pass by reference very briefly here. And it's worth, I included a link to Godbolt here, clicking to see that pass by reference in C++, well, it has to work by pointers, okay? But we also have this thing here, const here, so we can sort of pay attention to why is it that when we pass something by reference that we can't reassign that reference to something else? Okay, so you can think about that in this example included here. All right, so I have my sort of if time allows here. This is my way to cheat when I'm giving a talk if I'm going too fast or too slow. But because we can have pointers to other functions and to other pointers, we can create some cool data structures. And this is sort of the common homework here, implementing a linked list data structure. So I have a sample here. Again, you're not going to be able to read the tiny code, but you can visit the link here and think about how to implement this, right? This is an interview question or just a great way to see or test yourself if you understand pointers here. Okay, so kind of wrapping us up here and then leaving a little bit of time for questions. I think we still need to know about raw pointers. In a sense, it allows us to appreciate some of the abstractions that we have, like the smart pointers. And it's always good to know about your foundations. And I would still argue amongst experts thinking about this, if you're using C APIs or trying to interface with these other libraries, it makes sense because those are your only tools in those C libraries, right? You're passing things by pointer and returning them. So we still have to think about those in terms of legacy code bases or maybe supporting lots of platforms. So it's always worth teaching the foundations. I hope this was helpful. We could and we should argue what order smart pointers versus raw pointers first when teaching beginners, but that can be a later discussion. All right, so some analogies. I'm just going to flip through these that I use in education. Thinking about pointers as a page in the book and the index pointing to that page can be useful. Thinking about, in our grid of memory here, thinking about mailboxes, we have an address, and the value is what's stored inside when we open the mailbox and dereference. And here's some of the talks, and as promised, this is the talk on Thursday that's going to continue a deep dive into smart pointers, which are really cool. All right, so thank you for everyone who's here, who's attended online and in present, and I'll take any questions and hang out with you folks. Thank you again. It's been a pleasure. Questions? Yeah.
So what are the trade-offs with using the new versus the make unique or make shared? Why would one do?
Yeah, I think one with the make like unique or make shared, one, it's kind of explicit, showing what's being done. Now, it's kind of obvious with new. It is able to handle better if there's some sort of exception that could happen if you're allocating. So the question was, what's the difference between when we allocate with new and make shared with the smart pointers? And I'll highlight that really quick here. Was in one of these examples here, where we had this at line 25 versus 35. The one at line 35, since we're, again, wrapping what's going on in make unique, can handle if an exception's thrown while the memory's being done. There might be more, but that's my understanding. Yeah. Yeah. Other questions? All right. Thank you, everyone.